So everyone, welcome. Today I'm going to talk about the new DeepSeek models, especially the DeepSeek-R1, which has come as the ChatGPT killer. So basically, DeepSeek-R1 is a model which does thinking and then answering. So you give the prompt as a question, and the model will actually process the question in a thought process where it iteratively starts thinking about the question, and then finally it will give an answer. So this is essentially what the model does. So let us dive into the details of how it is and why it is such an important thing. So training LLMs. So how are the normal, like the most of the LLMs trained? So LLMs, how it starts is we have a transformer-based architecture, which is an untrained model, and then we train it on a large data set, basically the entire internet, in the task of language modeling. So language modeling is the task where given a set of words, what is the next word? So the next word prediction is called language modeling. And this is basically done using self-supervision. So you don't need an annotated data set for this. This is a fairly easy thing. The only thing is we need like large amount of training data. So once the model is pre-trained on this entire basically internet, you get this base LLM. Now, the second stage is supervised fine-tuning or SFT. Here, we like because a model that is just trained on just text data from the internet, it doesn't know how to respond to the prompt by a user. So you need to teach the model instructions like to behave like a chatbot, basically this conversational ability. So what we do is we train this on very high quality like instruction data. It's called instruction fine tuning, where with a large corpus of very high quality instruction data of chat based conversations is fed to the model, and the model is trained in that. So we will reach the stage of instruction tuned LLM. Now, any LLM which is instruction tuned, it has to be aligned to human centric conversations. And that is done mostly through the next stage. In ChatGPT, this was done using the RLHF, which is reinforcement learning through human feedback, where a reward model is trained using annotations by humans, and the output by the instruction tuned LLM is then passed to this reward model, which will give weighted rewards for each instruction for each output, and the model is trained based on that. For a very human-like output, it will give a very good high reward, and a reward that a output that is like very non-human centric or harmful. The reward model will give a very low reward, and this is called preference tuning. So this has been the way LLMs have been trained, and this is how Llama, GPT-4, everything has been trained. Now, let us come to the next stage. So this is a slide from Jensen's presentation of one of the 3 scaling laws of deep learning. So earlier, the performance of a model was scaling with respect to increasing pre-training data, which is called pre-training scaling. After that, it was found that more than pre-training, high quality post-training, basically the instruction tuning data was actually, and even the reward model RL was actually giving better scaling, which is the post-training scaling. And now with GPT-4o, which is a reasoning model, test time scaling has become a new thing, which shows that like the scope of scaling the performance of LLMs can be further enhanced using increasing the test time inference, like the test time compute time. So what is test time scaling? So a Google DeepMind paper, scaling LLM test time compute optimally can be more effective than scaling model parameters. So rather than making the models bigger, test time scaling can actually give better models without increasing the model size. So what is test time scaling? So language models basically, like I said, it is trained on this language modeling where given a series of words, it will predict the next word. But let us say we give a complicated question for the model to work. Then the next word prediction might not be exactly what the model needs to start answering. Because the moment humans are given a complex question, we don't suddenly start blurting out the answer. Humans actually need more time, and we do the stepwise, okay, like how you solve a math problem. We have to start from step A, step B, step C to reach the solution. So inference time scaling is a way to actually mimic this behavior in an LLM. So what it does is it allows more compute at inference. It allows the model to think, and the thought of a model follows this chain of thought reasoning, where the model will start from step A to step B in a sequence of steps to reach the solution. And it has been shown to give very good performance in reasoning tasks. And this is the process that works in OpenAI O1 and now recently in O3. So for inference time scaling, there are two ways that it was done. One was process-based reward and outcome-based reward. So in process-based reward, each step or each intermediate step to arrive at a solution needs to be evaluated. And if the intermediate step is right, we will reward the model higher. And if the intermediate step is low, we will lower the reward. So every intermediate step is actually evaluated. But in outcome-based reward models, we only look at the final solution. And if the final solution is right, then we give the reward. Otherwise, we won't. Now, I don't know how many of you are familiar with reinforcement learning. So I will just give an overview of what reinforcement learning is and how it works in the LLM context. So reinforcement learning basically is an interaction between an agent and its environment, where let's say a human being is an agent, and the room that I'm sitting is an environment, and like whatever I can see are the ways the environment reacts with me, and how I can move around is the way that I can react to the environment. So here, the agent is the LLM, and the state is the current prompt. So imagine like I am giving this particular prompt to the LLM. So Shanghai is a city. So this prompt is the current state, and the action that the LLM should do is next word prediction. And the reward will be like, well, let's say there are multiple predictions that the model can make with different probability. The reward for the model will be high if the probability of predicting the correct answer is higher, and the reward for the model will be low if it predicts the wrong word as the next word. So in reinforcement learning, the entire task is to make sure that the agent follows a sequence of actions that will give the highest reward. And in the normal reinforcement, like in the games and everything, the the harder part is actually creating the environment and actually calculating how the model should be rewarded. Like how will we know like this particular action that the agent is doing, whether it will actually give a good reward or a bad reward. So in LLMs, what normally we do is we have a separate LLM that is a reward model, and the output of the first LLM is given to the second LLM, and the second LLM actually evaluates. Oh, okay, this output, does it make sense or not? If it makes sense, let us give reward as a good reward, and if it's a bad reward, then it will penalize it. This process is actually optimized using a algorithm called policy gradient optimization. And this is basically how ChatGPT GPT-4 was actually trained, which is the reinforcement learning with human feedback, where the reward model was another LLM, which was actually trained by human annotators data on whether the output of an LLM is actually more human-like or not, or whether it has toxic content or not, and stuff like that. Any questions? on reinforcement learning? Because I know it's a very fast introduction. If anyone has any doubt.
Hey, Pranav,
So human feedback.
Yes, sir, go ahead.
No, I just wanted to. So human feedback is basically once the humans have rated it, then that's basically triggers the whole reward chain, correct?
So actually what they did was initially after instruction tuning, the GPT-4 actually gave a lot of output. So they made human annotators rate the output, and then that the input and the output by the human annotators was used to train a third LLM called reward model, and that was used to then do RL with the instruction tuned ChatGPT for getting the final one.
All good. Thanks.
Yeah. Ravi?
Yeah, I was just asking that this reinforced learning was used in the second step that you are fine tuning, or in the first step of fine tuning after LLM?
Like
The
this,
first stage.
it's here there is no
Yeah.
reinforcement learning. Here also
Okay.
there is no reinforcement learning. It's only here where reinforcement learning comes.
Okay. Fine. Okay.
So going ahead, like I will just explain what chain of thought is. So chain of thought is a way of prompt engineering where instead of asking, let's say I want this LLM to give me the solution for x square plus 2ab plus b square equal to 0 or something, or x, like solve a differential equation basic or a quadratic equation. Instead of directly asking the model to compute the answer, I will ask the model question step by step. What is this? Okay, then it will do the first step. Then I will ask the second. So it's a way of like breaking down the prompts as a sequence and feeding into the model one by one. Why it was done is because it helps the model analyze better, and it is also very easy to troubleshoot where the LLM is actually going wrong. And this is the heart of inference time scaling. Now I will actually move to the actual paper, which is the DeepSeek-R1, and we will just walk through the paper, and when needed, I will switch back and forth. So this is the DeepSeek paper, DeepSeek-R1, incentivizing reasoning capability in LLMs via reinforcement learning. So what they do is they create two models, which is DeepSeek-R1-zero and DeepSeek-R1. And DeepSeek-R1-zero is a model trained via large-scale reinforcement learning without supervised fine-tuning as the primary step. So it doesn't use any supervised training data. And what they found was DeepSeek-zero naturally emerges as a with numerous powerful and intriguing reasoning behavior. So for reasoning tasks, it was very good, but it encountered challenges such as poor readability and language mixing. So, but it could not do any other general purpose tasks that other LLMs were doing. So to enhance the performance better, they introduced DeepSeek V1, which incorporates a multi-stage training and a cold start data before the reinforcement part. And it is like performing better than OpenAI and everything. So let me go. So what they are telling is post-training has emerged as an important component for the full training pipeline. It has shown to enhance accuracy in the reasoning task, align with social values, and adapt to user preferences while requiring relatively minimal computational resources against pre-training. So this is why post-training was preferred over pre-training. You don't need that much data, and it actually helped in aligning better with the human needs. In the context of reasoning capabilities, OpenAI models was the first to introduce inference time scaling by increasing the length of chain of thought reasoning process. This approach has achieved significant improvements in the reasoning tasks such as mathematics, coding, and scientific reasoning. So in this paper, they take the first step toward improving language model reasoning capabilities using pure reinforcement learning. Without any supervised data, focusing on the self-evolution through pure RL process. So what they basically is doing is like they did two things: a pure reasoning model, and then how to use that reasoning model to create new data, which can be used for supervised fine tuning for the second model, which is the R1. So in both sense, like they first created a model that can learn purely without any training data, and then create using the first model, they created a new model which also does not require like as much new training data as needed compared to the previous LLMs. So basically for the first part, which is DeepSeek-R1-zero, which is pure reinforcement learning model, they use this algorithm called the group relative policy optimization. For this, I will actually show the original paper which introduced the group relative policy optimization, which is DeepSeekMath. So this acts funny enough, it came in 27 April 2024. And at that time, nobody paid much attention to this. So in this, it's a math model, and they used this particular optimization, this reinforcement learning algorithm to actually train that. Yeah. So before group relative policy optimization, most of the models were trained using this method called PPO, or proximal policy optimization. And this is the objective function of the proximal policy optimization. So what basically it does is, in proximal policy optimization, like I said, from a group of queries, we sample a query, and for that query, so the pi is the policy, or policy is the LLM, and we generate the output. So the output given the query queue, and with that output, so theta alt is basically the current iteration of that model, this current model state, and it predicts the output, and then this particular term, which is a ratio between the current model and the next model, or like the current model and the previous model, and it compares the two policies, and it gives an advantage. So this advantage is how the reward is actually modeled into the objective function. And for computing the reward, this proximal policy optimization requires a separate LLM. Like I said, a reward model is actually trained, and that model, show the picture. Yeah. So this is proximal policy optimization. The question goes to the model generates the output, and the output is then given to the reward model. The reward model generates the reward, and then there is a value model. So we don't directly send the reward to the objective function. We compute something called an advantage. And advantage is different from the reward in a way because advantage is actually, you need a baseline. So let's say a model is actually giving, the reward model gives the reward, but we don't know how relevant that reward is with respect to other rewards or other rewards the model can give to other outputs. So a baseline has to be first computed, and for that a new model is required called a value model, which will, for the same output, it will create a value, and the both reward and value. So this is the reward, and the value will be considered as a baseline, and using both of them, an advantage is actually computed, and then that is like given to the policy, and that is used to train the model. So this value model and policy model are both iterated while training, and that actually makes the training process much harder. So the value model, so in here, this is the reward that is computed, and they're telling in PPO, a value function need to be trained alongside the policy model, and to mitigate over optimization of the reward model, the standard approach, they also add this. So this reference model is actually, so let me give an example. Let's say I have a llama model, a fine-tuned llama model ready. Now I want to do proximal policy optimization on the llama model. So the fine-tuned llama model, if I call it llama 0, the reference model is that llama 0, the 0th iteration. And the policy model will keep updating. It will become llama 1, llama 2, llama 3 in each epoch, but the reference model will still be the original weights of the initial llama 0. And why they do the scale divergence is so that it can stabilize the training and the model won't be very far away from the original. So in the context of PPO, the main issue was they needed to train simultaneously a value model and a policy model. So now what they do using group relative policy optimization is they remove the need for a value model. And what they do is something clever. So just like earlier, instead of they have one question, they sample one question from the prompt and they pass it to the policy model. And instead of generating a single output, they compute multiple outputs. And that is passed to the reward model and it will generate multiple rewards for each output. Now, because value model is used to compute the baseline, here they completely remove the value model, and for computation of the baseline, they just average the reward of all the outputs and use that as the basically they do the normalization of the rewards and use that as the baseline, and that is why it is called group computation. So here is the this is the computation of the advantage. It's just a normalization. And all the other terms. So basically, this is the important term. This term is the KL divergence between the original model and the current iteration. This is actually just a clipping term that is added so that the model, sometimes what happens is the reward can be or advantage can be too high that it will push the model to deviate too much. And to stop that deviation or control that deviation, a clipping is added on the entire policy optimization. So that the stability of training will be better. So all the other terms are basically for stability, and basically they just remove the need for a value model and just they are basically resampling like multiple outputs and just normalizing them to get a baseline. Any questions in this? I am sure that there will be a lot of questions, but I'm just trying to give an overview of it because it's a very complicated equation. But I hope you understand an overview of it.
So here, if I understood it correctly, this advantage is relative to all the other things in that group. Is that correct? Is that how to
Yes,
think
sir.
about it?
Yes, sir.
Okay.
Yes, sir.
Whereas otherwise it was absolute in the previous.
Otherwise, it was not absolute. You needed another model to compute what is the baseline. So it will be computed relative to the baseline, but we didn't know what the baseline was. Here, the average of this reward is the baseline.
Got it.
Yeah. It's a very simple thing, but it's it actually reduced the training by half. Because you don't need one actual full-fledged model for this.
Nice.
So now coming back to the R1, maybe I think, yeah. So here is what it does. This is the GRPO, and here the reward, just compute the mean of the group and divide by standard deviation, and that is the advantage. And the advantage is multiplied with the ratio of the current policy with the previous policy. And if the current policy is better than the previous policy, the advantage will be higher. If the current policy is worse than the previous policy, it will be lower. And it's just like maximized over the entire thing, subject to these constraints. That the previous and the new policy shouldn't like vary too much, and the original model and the current policy shouldn't also vary too much. So in very simple terms, this is what it does. So now the basic question is, why didn't this particular task require any fine-tuned data? So what they did was the rewards that basically the prompts or the question answering tasks that they choose was very clever. They only choose certain questions for which the answer was deterministic and always correct. So problems like math problems, with deterministic result. And the model is required to provide final answer in a specified format, enabling reliable rule-based verification for correctness. Similarly, lead code problems where a compiler can be used to generate feedback based on predefined test cases. So basically, the task was I will just show one more thing, and format of the reward. So the model shouldn't just give the output, the model should also think, right? It should give the thinking, the chain of thought reasoning. So in addition to the accuracy, they also employed the model to generate output in this format. So the user asks a question and the assistant solves it. The assistant first thinks about the reasoning process in mind and then provides the user with an answer. The reasoning process and answer are enclosed within like think and think start, think and token, and answer start, answer and tag respectively. So the model is given reward when like something like this is actually there in the answer. Like it should start with thinking, it should end, thinking should end, then answer should start and answer should end. And the answer here is the only thing that is actually evaluated for accuracy. So there's only a format reward and accuracy reward. So what actually happens here is not actually evaluated by the model in the thinking part. So so we did not apply the outcome or process neural reward model in developing DeepSeek-R1-zero because we find that neural reward model may suffer from reward hacking in the large-scale reinforcement learning process, and retraining the reward model needs additional training resources and it complicates the whole training pipeline. So if process reward had to be given, then this particular part needs to be evaluated in each step to see whether the model is actually like going through the right steps. But since they are only looking at the answer, they could actually like overcome that step. Like they need to do this particular step here, which actually saves a lot of like training data, because this part, especially for coding problems and maths problems, this is a very easy way to just check whether the answer is correct or not. Now, basically, they just trained this particular task in reinforcement learning and just let the model run reinforcement learning iteratively. The base model was a DeepSeekV3 model and a pre-trained DeepSeekV3 model, which was already there. And they just took it and just did reinforcement learning without any external data in this particular task. And what they found was this. So as the number of reinforcement learning steps increased, the performance of the model started increasing. And more than this, the more interesting result was the length of the response also started increasing. Basically, the model is learning that if it thinks if it actually takes more time to think, because the answer part will always be short. Only the thinking part is the part that actually should increase. The thinking part should keep increasing, right? The model actually learned that the reward will be better if it actually starts thinking longer and longer, and it will actually give it better and better result, and without any interference. So the self-evolution process of DeepSeek-R1-zero is a fascinating demonstration of how RL can drive a model to improve its reasoning capabilities autonomously. By initiating RL directly from the base model, we can closely monitor the model's progression without the influence of supervised fine-tuning stage. This approach provides a clear view of how the model evolves over time, particularly in terms of its ability to handle complex reasoning tasks, as depicted in Figure 3. Which is this. Throughout, the improvement is not only the result of external adjustments, but rather an intrinsic development within the model. DeepSeek-R1-zero naturally acquires the ability to solve increasingly complex reasoning tasks by leveraging extended text time computation. This computation ranges from generating hundreds to thousands of reasoning tokens, allowing the model to explore and refine its thought process in greater depth. And what they found was a lot of self-evolution of emergence of sophisticated behavior in the test time computation started increasing, like behavior such as reflection, where the model revisits and reevaluates its previous steps, and the exploration of alternative approaches to problem solving arise spontaneously. These behaviors are not explicitly programmed, but instead emerge as a result of model's interaction with the reinforcement learning environment. This spontaneous development significantly enhances reasoning capabilities. And here is what they tells about the aha moment. So basically, like, this is what they're telling, like, it's actually thinking how to solve this equation. It does it one way, and it reaches a point, and then it's like, wait. That's an aha moment I can flag, and it reevaluates this step by step, and it just basically both are correct. They just switches the side, like from here it just switches it this way, and so basically the model realizes something in between and then goes back to try that. So these kind of behaviors started emerging. So it underscores the power and beauty of the reinforcement learning rather than explicitly teaching the model on how to solve a problem. So then, what are the drawbacks of DeepSeek-R1-zero? Basically, other than reasoning, it cannot do any other task properly. It was not even as good as the DeepSeekV3 model, which was the initial model or the baseline model on which this was done. So they thought, okay, for other general purpose tasks, we need another model, but how can we use DeepSeek-R1-zero itself to create a much better model? So they did this 4-stage process, which starts with what we call cold start. So what is cold start? So now that they have trained the DeepSeek-R1-zero, they use DeepSeek-R1-zero to create data on which the new model can be trained. So basically, since DeepSeek-R1-zero is very good at reasoning, especially long amount of chain of thought reasoning, they actually ran DeepSeek-R1. We construct and collect a small amount of long chain of thought data to fine-tune the model as the initial reinforcement learning actor. To collect such data, we have explored several approaches using few-shot prompting with a long chain of thought as an example, directly prompting models to generate detailed answers with reflection and verification, gathering DeepSeek-R1-zero's output in a readable format, and refining the results through post-processing by human annotators. So basically, they fed a lot of prompt to DeepSeek, generated the response of DeepSeek-R1-zero, and then made humans clean it. So basically, it is elimination sampling in some sense. And that became the data set on which the first stage of, or what they call cold start. Cold start is they take a new DeepSeekV3 model, a base model, and then use this new data that is generated from DeepSeek-R1-zero to train it on in supervised way. Is it clear till here? Any question? So the next part is reasoning-oriented reinforcement learning. So after fine-tuning DeepSeekV3 based on the cold start data, we apply the same large-scale reinforcement learning process employed by DeepSeek-R1-zero. So this phase focuses on enhancing the model's reasoning capabilities, particularly in, so they do what the previous GRPO on the new model after the cold start. And what they observed is similar to what DeepSeek-R1-zero also exhibited. It was actually very good in reasoning, mathematics, science, and coding, but it exhibited language mixing and other issues. So what they basically now did is rejection sampling and fine-tuned, supervised fine-tuning. So now, till now, the model has only seen like reasoning-based data for training and reinforcement learning. So they kept on generating more reasoning data similar way. We expand the data set by incorporating additional data, some of which was used to generate some of which use a generative reward model by feeding ground truth and model predictions into a DeepSeekV3 for judgment. So now they are actually using different techniques to get more data, but they use their own models for generating it. And in total, they collected some 600,000 reasoning-related training samples. For non-reasoning data, they use the same data that they used for training DeepSeekV3. and they reuse portions of the supervised fine-tuning dataset of DeepSeekV3. And this was around 200,000 training samples that are unrelated to reasoning. So all in all, the fine-tuning was done based for 2 epochs in a dataset with just 800,000 samples. Now, once these 2 stages, this kept happening iteratively. And finally, they did a final reinforcement learning, which is similar to the reinforcement learning with human feedback, where they have a reward model. Actually, they have 2 reward models, one for helpfulness and one for harmlessness, which actually makes the model generate so what they basically do is we focus exclusively on the final summary. So whatever output the model is generating, they summarize it and they do this analysis. Actually, a different model does the analysis for the utility and relevance of the response to the user while minimizing interference with the underlying reasoning process. For harmlessness, we evaluate the entire response of the model, including both the reasoning process and the summary, to identify and mitigate any potential risk, biases, and harmful content. And then they're talking about distilling. So this actually then shows how the model is actually better with distillation and everything. And let me just go back to the PowerPoint slide to show how this model actually is working. Till now, is there any doubts?
Pranav, hello.
Yeah. Yeah.
I had a couple of doubts in this. One is like in the training of DeepSeek-R1, there was this thing token that was being used. It's just the thing token that was the kind of the main motivation for, or the chain of thought prompting was actually induced by this thing token. Is it deliberately introduced like that?
Yes. So
okay. So
yeah.
Yeah. So and the other question was like in that group called GRPO optimization, you said that the average of so there were like many outputs coming O1 to ON was there, and then we computed like what was the average reward and what is happening in that. So and you also told that only the final answer was actually was looked into and was final answer was actually looked for the reward, like the only the small part was only looked for the reward.
Yeah.
So my question was, when there were like different responses that were generated, and only the final a small portion was only evaluated. So each of these O1 to ON generated different answers, and then we were looking back. Is that correct?
Yes.
Okay, and then so we were looking back and saying that whichever is below the average, we decrease the reward, and whichever is above the average, we increase the reward.
Yes.
Okay. Just to clarify. Okay.
Yeah. Okay. So actually, this is the DeepSeek R1-zero training regime. Basically the GRPO. So basically, it's like a DeepSeekV3 base. And then it just goes through this reinforcement learning loops where there's a training prompt. This is the current checkpoint or the current policy. It will generate like 4 different, let's say multiple solutions it generates. And then it takes the average reward of it. And then that will be the new baseline. And then it will compare it with all the other ones and assigns an advantage score for each of them. And that is used for policy gradient optimization. So this is basically what GRPO does. Now here, this is the full training pipeline. So this reason-oriented reinforcement learning is the GRPO. And this interim reasoning model is our DeepSeek R1-zero. So what they do is for the cold starting, they will use this DeepSeek R1-zero to create the reasoning data, which is long chain of thought examples, around 600,000 examples. Now you have this DeepSeekV3, a new DeepSeekV3 base. This is first trained on this particular thing. That's what we call a cold start. And then after that, it is also made to undergo this GRPO, the reason-oriented reinforcement learning. And after that, this like SFT, supervised fine tuning. This is the data that they used for training DeepSeekV3 base earlier, which has language modeling like chat, the normal natural language data sets, and they add it with the more of this like COT data sample generated with DeepSeek-R1-zero, and then fine tune it. So you get this SFT checkpoint, and this is then like a general reinforcement learning is done, in which there are two reward models, like which actually helps in helpfulness and harmlessness and everything. And this entire thing is kept on like iterated to get the final DeepSeek-R1. So the highlight is they first created a reasoning model that can be used to get better reasoning data, which will actually reduce the need for reasoning data. And they show that with very limited number of supervised fine-tuning data, they can actually beat OpenAI. So this actually reduces the data requirement, the compute requirement, a lot of the other hi-fi stuff that OpenAI claims that it needs. It doesn't need any of it. And another one more thing is, in the paper, they have not mentioned how much time they actually like or money they actually took to or compute they actually took to train this final DeepSeek R1. That also I just want to put it out there. So this is like the general, yeah.
So one question, overall, it seems like they have actually got a very good quality data. They have actually created a very good quality data from a reasoning model they have built. And this good quality data was used in SFT, and then finally the rest of the procedure was almost similar to the other LLMs, right?
Yes. So what happened was, because the quality of reasoning data was very good, the amount of other data, like supervised training data that was needed, was very less compared to other models. So they don't say that they only use the reasoning data. They actually use other data also, but that was much lesser than that was needed for actual like Llama or OpenAI or stuff like that.
But they were using in the cold start, they were using again DeepSeek V3 to start with, right?
Yeah, for the cold start, they were only using reasoning data. Yeah.
Okay.
Yeah. So this particular general reinforcement learning phase is like shown here, where there are reasoning prompts. So this is the reasoning prompt, and this is general prompt. So general prompt is actually fine-tuned data that is curated from the very high quality data that they had to actually do, just like other LLMs. But the amount of general prompts was very less. Like very less was needed because of the reasoning prompts, which they actually generated using DeepSeek-R1-zero. And this was actually verified, like this in this general reinforcement learning, there were two other models, the safety reward model and helpfulness reward model, which I think was again trained using human annotations and everything. But all in all, because most of the other things were generated using their this GRPO, the amount of general prompts required and the amount of data required for building these two models are much lesser compared to Llama or OpenAI. I think that is what I am getting out of it. Any questions? I know like it's too much information in too less time, but can I go ahead?
Yes, please.
Yeah. So next I want to go to the architecture. Architecturally, the innovation in R1 is not actually, there is no architectural innovation. This is mostly training innovation. But the actual, so the claim of that training only taking $5 million is actually because of this architecture, which is the DeepSeek V3. So I want to go to the DeepSeek V3 paper. And this paper is a marvel in architecture, in the sense like they have looked at every possible way to make the model efficient. So DeepSeek V3 is strong. It's a mixture of expert model with 671 billion parameters in total, with 38 billion activated for each token. So to achieve efficient inference and cost-effective training, they also have this multi-head latent attention and the mixture of expert architecture. So which was also used for DeepSeek V2. On top of that, they have an auxiliary loss-free strategy for load balancing across the multiple experts, and they have a multi-token prediction training objective for better performance. So they train V3 on a large quality data. It shows that it can outperforms other open source model and achieve comparable performance to leading closed source models, basically ChatGPT. And it requires only 2.78 million H800 GPU for its full training. And the process is very stable. So this is the famous graph that everyone has seen. So now I will go to the interesting parts in the architecture. So the first thing, for efficient training, they use FP8 mixed precision training and implement comprehensive optimization. The low precision training has emerged as a promising solution for efficient training. As for training framework, they have this dual pipe algorithm for efficient pipeline parallelism, which has fewer pipeline bubbles and heights. So basically, when it is switched to multiple GPUs, the parallel processing, they created a new algorithm which actually reduces the the time of computation. Like the tensors will be sent to like different outputs of different layers will be sent to different GPU, so that the first layer will be free for the next forward pass and backward pass and everything. So very optimized training strategy. And also they maintain a constant computation to communication ratio, fine-grained experts across nodes. Like even I don't understand most of these things, but they create a lot of communication kernels to fully utilize the InfiniBand and NVLink bandwidth. So they basically optimize the memory footprint, and they also have this. They don't like store the tensors and then retrieve, because IO like actually that takes actually more time. So they do recomputation in the backward, like flash attention, where it's a hardware aware algorithm, basically where recomputing the output of each node is actually faster than actually saving the output in memory and reclaiming it for backpropagation. So yeah, so this is the training cost of DeepSeek V3, which is like they are telling it's like $5.5 million. So this is for pre-training. See the computational cost of pre-training and post-training. So post-training, which is training with the supervised fine-tuning on high-quality data, is actually like minuscule compared to the actual pre-training on the large like internet kind of data. So this is basically the paragraph that they say, right? Like they during the pre-training stage, on each trillion token requires only 180 H800 GPU hours, which is, and our cluster with 2048 H100 GPU. So this is the cluster that they have used. And yes, load balancing and multi-token prediction. Let me now go to the architecture. So this is the architecture. Yeah, this is the DeepSeek architecture. So now I want to just focus attention on the RMS norm part, because this has now become the standard normalization across all LLMs. We are using layer norms and everything still, but I think we need to switch to RMS norm now. Then in attention, they have this multi-head latent attention. So basically what it does is there's a latent vector that for the KV cache, and from that the key and value vectors are generated, which is actually a lower dimension than actually storing the whole thing in the input dimension. And then they compute the output. So basically it's a what you say, a dimensional reduction mechanism. And the computation of attention itself has been during inference has been improved using LoRa and the similar stuff. And the mixture of expert model, that is in the feed forward network part. So in the feed forward network, we know there is an MLP layer. So they have multiple parallel MLPs, and so these are called different experts. So there are like N experts And there are routed experts and shared experts. So shared experts are experts where the output always passes through these experts no matter what. And the routed experts are experts where there's a router which will actually select for a particular generating a particular output, which like not all the experts needs to be activated. Only few of the expert, like top K expert, has to be activated, which is why a 600 billion parameter model will become somewhere around like 30 billion parameter model during inference. And so this is the like architecture. And so this is the multi-token prediction. Basically, at each step, instead of generating the next token, it actually generates like like multiple tokens in advance. And that actually in the next time also it actually, so here it's T1, T2, T3, T4. It just has to it generates all the previous tokens also along with it. And so basically what it basically does is it generates multiple tokens in advance, and that all those generated tokens are also fed along with the input to get a better performance. So I will show you that pipeline. Yeah, so this is the dual pipeline scheduling, where like I think this is like each layer, like how after the first tensor is done, like it passes to say next layer, and next layer tensor will be run on another GPU in parallel and things like that. So in basically the idea is to reduce the number of white spaces when running GPU parallelism. And this is one of the efficient implementations. And the paper talks a lot about different kinds of efficiency improvements that they have used in this particular architecture while training. So I'm not going, I just want to show the architecture. That's why I showed this paper. Like everyone should definitely read this paper. It's like very good. Now coming back to, yeah, so here is a simpler way of like looking at the architecture. So basically there's a tokenizer that converts the language to the tokenizer, the model dimension. So the embedding dimension of the vector is like 7,168, and there are multiple transformer blocks. So initially the transformer block, there will be like a few of them, which is the normal transformer block. And then comes the mixture of expert transformer block. So the first three are normal transformer block. And then there is like, so basically the next from 4 to 61 are this mixture of experts transformer block. And this blue ones are the ones that are active in this particular figure. So this is, and then there are like shared experts which are always active. So this is the overall architecture. So this is the conclusion. So basically with the coming of DeepSeek, like the entire stock of NVIDIA and the entire AI in the US AI market just crashed because of this efficiency that actually came with all the, like it broke all this hype that you need like a lot of data, a lot of compute, and scaling is the only way to get better performance. And I think that is why this model and the architecture and the training routine and everything is so important to understand. And on top of it, I just want to show one more thing. So I am actually showing a live demo of DeepSeek-R1 distill in my laptop. So you can all download this LM Studio and it will just load the weights directly and save it in your laptop so that you don't have to worry about China stealing our data. And so these are some of the questions that I asked. So because one of the serious claims that came in the news was, if you ask whether Arunachal Pradesh is a part of India, the official website will tell some like bad responses. But when I download the weights and I ran the like the query, it actually is giving the correct answer. So, and this is the chain of thought reasoning that actually, like you can actually follow it and see how it is generating the result. So this is the thinking part and this is the answer part. So yeah, so like I can ask like write a code on image classification in PyTorch, and it will start like running. Of course, it's running in the laptop, so it will be slow. But yeah, this can be used. So once the prompt is processed, it will start the thinking process. And if you click, you can see the thinking process happen in real time. And yeah, so I think like anyone has a question, we can answer.
So it seems like the censoring they have put on the website is after the training. Like the model
Yes.
doesn't have the censoring. So
Exactly.
it's a separate guard. It's a separate guidelines they have.
Exactly. It's a separate guardrail that they have put on top of it. The actual model doesn't have like censoring on it. I think because it is
But
running
I
in
mean,
China. Yeah.
but then it's very funny to think that everyone can download the local model and then host
Exactly.
it, and then yeah.
Exactly. And the reasoning is like pretty well, like as we can see, like it's actually going through how to create the code for it and everything. It's pretty fast also. So it is thinking. It has not yet started answering.
So can we have the other mode, like not without the deep thinking? Like can we have the in the local model? Can we just get the plain answers? Like in the website, there is a uh, there is the option to not to deep think and get us the straight answer, right? In DeepSeek website.
I haven't tried whether it is here in this, but LM Studio has like multiple choices. Like so, because this is a chain of
Okay.
thought model, it does this always. I think I haven't checked
Yeah,
all
but
the
that
features.
yeah, but the responses are like too different when we are getting it with the what do you mean, like the thought and without the thought.
Yeah. So here we see, right, weight, but I should also think about this weight. So I think the way they are claiming it is all this the model learned by itself. Like, oh, I forgot about it. Oh, wait, and everything. This is that aha moment they are doing, like another thing. And so they are claiming all this was emerging automatically out of reinforcement learning. This was not actually fed to the model explicitly.
So this is what we
Yeah,
advise in interviews, that please also think aloud to show your reasoning,
Yes.
right? So that's going in that direction.
Yes. Now it has started answering. So yes, this is how this. So I actually think this is a very. I don't want to take the word revolutionary, but I think it's a watershed moment in the creation of architectures.
Sputnik moment.
So any thoughts on whether this chain of reasoning can also be used for visual reasoning, maybe for vision related tasks? Like
So
in pathology, we can think of, okay, I see that these cells are not, they don't look normal. They look like the nuclei are too big and so forth. You know, something along those lines. But I think the back end, the foundational thing will also have to be trained on a lot of this visual data with
yes,
text descriptions.
yes, sir. And because there was a lot of this easily available math problems and code problems, like they were able to do this reasoning very efficiently. Similar something we have to find in terms of visual domain that can be easily used to train an RL algorithm without actually needing like very high quality annotated data. If that is possible, then using that, maybe we can create also more data.
Right. So I think a lot of vision language paired data will be needed.
Yes. And very interesting work. Anyone else have any question? I am sure like lot of things are like not understood. I just ran through it like very fast. But overall, the logic of the algorithm, is it clear?
So I have a small question. So how they started with a reinforcement learning model. What was that? Like which
DeepSeek
model did
V3.
they use? And
DeepSeek
Okay.
V3.
No, the first one. Like it started with, I mean, DeepSeek-V0. That one.
No. Everything is DeepSeek V3. The DeepSeek-R1-zero is also started with DeepSeek V3. The DeepSeek-R1 also starts with DeepSeek V3. Even the helpfulness and the harmlessness models are also DeepSeek V3. Everything is DeepSeek V3.
And this architecture is based on
DeepSeek V3.
Okay, they have created a architecture by themselves.
So this is DeepSeek V3 architecture. Okay, this is not so because DeepSeek-R1 is actually the fundamental architecture is DeepSeek V3. It's written DeepSeek-R1, but this is DeepSeek V3. So these safety reward model and helpfulness reward model are also DeepSeek V3. This SFT checkpoint is also DeepSeek V3. The DeepSeek-R1-zero, the base is also DeepSeek V3. The entire thing is DeepSeek V3.
Okay. What
And
about the reinforcement learning? How are they while generating the V0? What was their data? Or I mean, they have to fit something, right?
Yeah. So for that they used math problems and code problems for which there's a clear answer. Yeah. You don't need an ambiguous thing, right? So for a mathematical problem, there is a clear answer. And for the coding problem also, it's like compiler coding. You will get they went through lead code and scrapped the data from there, I think.
Okay, that makes sense. First, they have made their model logical and then they started to train with other data.
Yes. And that is what they showed. If you train first on logical reasoning stuff, then you don't need much supervised fine-tuning data.
Okay.
Yeah.
So the SFT doesn't have any novelty, right? It's just the next word prediction only.
Yeah, that is next word prediction only. No novelty in SFT. That is exactly what the other models are doing. Even the general reinforcement learning is also same as what GPT-4 and everyone is using. The only thing is the reasoning prompts are generated by themselves. They don't need anything new to generate it. And they are telling even for general prompt, they used DeepSeek V3, a pre-trained DeepSeek V3 LLM to actually create this in some sense. And I just want everyone to realize that it is the training of the DeepSeek V3, this paper, this model which is actually the $5 million one, not R1. But even then, this is a very huge technological innovation in terms of efficiency. Yeah, I recommend everyone to read all these 3 papers. This is very.
So I think even here the 5 million claim is a bit misleading because I don't think they would have trained only once.
Yeah, so they don't claim that in the R1 paper. Just because the base model is V3 and in V3 they say it is 5 million, everyone just is like, oh, V3 is 5 million. So DeepSeek models are 5 million. They don't claim that in the R1 paper anywhere, that it's actually, they don't mention the cost or the compute or the training amount of training data they say, but the cost and compute they are not telling or what GPUs they used. Yeah.
Must be multiple hyperparameters they would have tested on.
Yeah. Exactly. But then even OpenAI is also not telling how much money they actually spend in training them, right? They are also a closed model. So yeah, I don't see the point of what you say, them asking others to tell, no, this is false, because they themselves are anyway not telling it. But one thing is very clear from the technical report is it's a very efficient model. That is clear.
So there are conspiracy theories that that has emerged saying that they had access to better GPUs and then they were training it on a larger model and then they finally what they showed as open weights are like the distilled model.
Yeah.
So
I am like, it serves them well. I am like, even if they have done it, I think it is like the OpenAI doesn't have any ethical or moral right to claim that their thing has been stolen, because they have been doing that while training the data, right? They have stolen data from countless people without any accountability and doing it. So I think it's karma. Yeah.
And H800 is not a lightweight GPU, by the way.
Yeah. But I think it is the only one that Chinese can import.
Okay.
Yeah. It's a very like a downscaled version of H100. It's or H200.
Oh, H200. But it's better than H100.
That I don't know. But like again, even in
So they-
that, they are claiming that they trained, at least the V3 model, they are claiming that they trained it in using just 2040 GPUs. It is much smaller than others in 3.7 days.
Right.
The pre-training happened in 3.7 days. The fine-tuned training happened in 2 months. No. I think the pre-training happened in 2 months. They are just comparing how many days it will be in terms of that. But overall, it took them 2 months to train. As a local model, because everyone has said that data is being leaked to China because of it, but nobody cared when OpenAI was using their data for training their model. Anyway, but still, if people are worried about their data being lost, it is always better to just use this LM Studio and run it on local system. And in here, you can not just use like DeepSeek. Any open source models can be run like this on locally. And it cannot do RAG also, like retrieval using, you can make it read a PDF and ask questions based on that and everything. It's a very good interface.
Fantastic. All right. Any more questions from anyone? All right. Thanks a lot, Pranav.
Thanks, sir.
Thanks to Keshav for last week's presentation. Okay.
I think we can stop the recording.
Yeah, I just stopped.